Okay, so today we're going to look at step functions and how they can be used to rewrite piecewise functions as a single expression. And we want to then learn how to take Laplace transforms with step functions and inverse Laplace transforms. And then we'll complete some examples solving a differential equation involving step functions. So we can rewrite, we use the letter u for a step function. We can use a subscript, say c, and so we say that the step function is 0 for times before c, and it's equal to 1 afterwards. So if this is our timeline, this is time c, the step function is equal to 0. Once we get to time c, it turns on and becomes 1. So you think of it as a permanent on switch. Time c, we go from 0 to 1. So for example, if I want to write that, okay, I have a function which is equal to some exponential, say, but only after some time, let's say time equals 1, but 0 otherwise, you could say, well, okay, I'm just going to take this exponential, and I'm going to multiply it by this step function which turns on at 1. But before time equal 1, the step function is 0, right? So before time equals 1 and afterwards. Okay, well, before the step function is 0, so you just get 0. But after time equals 1, this becomes 1, so you're just left with your exponential. It's like we want to turn on this decaying exponential, but only after a certain time. This step function can also be used as an off switch, right? If suppose you want a function, okay, and it's equal to, say, sine of t, but only if t is between, say, pi and 2 pi, but 0 otherwise. So what we can do is we can say, well, we're going to turn on the sine time pi, but we're going to turn it off at 2 pi. So we're going to take the step function times sine of t, and let's see whether that works. Using these two step functions, we naturally partition the timeline into 3 intervals. So before pi, between pi and 2 pi, and after 2 pi. So now if t is less than pi, by definition, the step function which turns on at pi is 0, and of course the step function which turns on 2 pi sometime later is also 0. So you get 0 minus 0 times sine is just 0. Times between pi and 2 pi, you have that this step function which turned on at pi is 1, but this step function which only turns on at 2 pi is still 0. So this expression, 1 minus 0. So you get 1 minus 0 times sine. And for times after 2 pi, both step functions are now turned on, so to speak. They're both equal to 1. The first step function minus the second step function is 1 minus 1. So 0, and then times sine is 0. The idea is that we have like this piecewise function. We can express it as a single expression using step functions. Here's a formulaic way of approaching this. So let me give you an example, another example here. So suppose we have a function. It's equal to 0 for times before 2. It's equal to 1 for times between 2 and 5. It's equal to t for times between 5 and 8. And then it's equal to t squared for times after 8. So what I can do is I can write this as a single expression by saying, well, we have 0 before this time, but at time equals 2, we have to turn on the 1, if you will, and turn on that piece. So we're going to take that piece and multiply it by the step function which turns on at 2. Now at time equals 5, we transition over to the next piece. So what we're going to do is we're going to, at time 5, turn this on. We're going to introduce this new piece, so times t, but then subtract out the preceding piece, so minus 1. And finally, we transition to a new piece at t equals 8. So we introduce a step function that turns on at 8. And then we want to turn this next piece on, but subtract out the preceding piece, so minus t. And then you can confirm that indeed this would give you this piecewise function. So in general, you want something formulaic. If your piecewise function consists of k pieces, so your function is defined by different pieces depending on the interval, it's always the formula where we just turn on the first piece. So we have g1, but then at time a1, we introduce a step function, and then add multiply by the new piece, then subtract out the preceding piece. At the next transition time, we again introduce the step function that turns on at a2, and then we add in the new piece that we want, but subtract out the preceding piece. And then we keep doing this until we get to the final time, a sub k minus 1. We have a step function turning on at the last kind of transitional time. We add in the next piece and subtract out the preceding piece of our piecewise function. So we'll do another example. So suppose g of t is equal to minus 1 for times before 0, and it's equal to 2 for times between 0 and 1. It's equal to sine of t for times between 1 and pi. Then it becomes, let's say, a decaying exponential after that time. So we have this, the g of t, we have this value for our function for all times before 0. But at time 0, what we want to do is turn on the step function at time 0, add in the new piece, but subtract out the preceding one. And we would continue this process. So time 1, add in the new piece, subtract out the preceding one. So finally at time pi, turn on this final piece, but make sure that we turn off or subtract out the preceding piece. So we use the step function to rewrite piecewise functions as a single expression. And we're doing this so that we can eventually take Laplace transforms of this expression. So we have to learn how to take Laplace transform of a step function and then a Laplace transform of a step function times another function. So let's look at the Laplace transform of just a step function just to see how this would work. Laplace transform of u that turns on at c. So we'll use the definition of Laplace transform. So this is the improper integral from 0 to infinity of our function times e to the minus st, and we're integrating with respect to t. But of course, we remember that the step function is defined to be 0 for t's less than c, this index. It's defined to be 1 for t's which are greater than c. This whole expression is just 0 until t equals c. So because here t is less than c on this interval from 0 to c, this is just 0. T is greater than c, this is just 1. So this goes away, and we end up integrating from c to infinity. So finding the antiderivative here with respect to t, we get, that's from c to infinity. And at the upper bound, at the limit as t goes to infinity, we get 0, and at the lower bound, did a little exercise here finding the Laplace transform of a step function just by itself. But you can do better. You can find a formula for the Laplace transform of a step function times a function of t. The step function, in a sense, is going to turn into this exponential e to the minus cs. Then we're going to multiply that by the Laplace transform of the function, but after we replace t with t plus c. So for example, suppose you have a Laplace transform turns on at 2, let's say 3, and your function is t squared. Okay, so what I'm claiming is you think of the Laplace transform of that step function as giving you an exponential in the s domain, e to the minus 3s, then times Laplace transform of function t squared, but you replace t with t plus the index here, so t plus 3. Before taking the Laplace transform here, I'll first FOIL this out. So t plus 3 squared is t squared plus 6t plus 9. Okay, so this will give us the Laplace transform of t squared plus 6 times the Laplace transform of t plus 9 times the Laplace transform of 1, so that's 1 over s. Now we are going to prove this, use the definition, and then of course because this is 0 for t less than c, we might as well start the integral from c, and then after time c, our step function is 1. Okay, so now we're going to do a change of variable. So in the definition, I need that improper integral to start at 0, right? So it looks like I maybe want to define a new variable, let's call it u, which is the original variable, t minus c. Now I chose this because I noticed that when t equals c, u will be 0. That's equivalent to saying, doing a direct substitution where t is equal to u plus c. Okay. And notice that dt is equal to du. So let's see what we get. F of t becomes f of u plus c. Likewise, t can be replaced in the exponential function with u plus c. And dt is now just du. And the bounds, when t equals c, u is 0. And when t goes to infinity, so does u. So the upper bound is still infinity. So now we'll use properties of exponents. Notice that this exponential here, it doesn't involve u. It doesn't involve the variable of integration. So we can pull it in front of the integral. Now u is just a dummy variable, right? It doesn't matter what you call it. So you can, if you'd like, we can go back and just say, okay, let's u equal t. So then you would recognize this improper integral from 0 to infinity is exactly the Laplace transform of this function here, f at t plus c. So that's our formula. So let's practice a little bit more. Suppose you want to find the Laplace transform of step function turns on at 7, and you have an exponential e to the minus 3t. So again, you think of this step function as being turned into an exponential e to the minus 7s. And then we would multiply that by the Laplace transform of this function of t, except we're going to shift t. We're going to replace t with t plus 7. And after taking advantage of properties of exponentials and linearity of the Laplace transform, we get the Laplace transform of e to the negative 3t, 1 over s plus 3. So let's make this a little tougher. Suppose you have e to the t times t cubed, and the step function is going to become an exponential in the s domain. And we multiply by the Laplace transform of this, but at t plus 7. So using properties of exponentials, I can just bring out the e to the 7. And we have e to the t times this business, so that's going to be t cubed plus 21 t squared plus 147 t. But then we know that Laplace transform of an exponential times this, that's just going to give you the Laplace transform of t cubed. So that's 3 factorial over s to the power 4, except we replace s with an s minus 1. The exponential function gives you a shift. Then we have 21, and then the Laplace transform of t squared, 2 factorial divided by s cubed, except s is replaced with s minus 1. So the next thing we want to do is practice finding inverse Laplace transforms. And so this is going to be usually something that looks like some exponential, like e to the minus cs, times some function of s. And you want to find the inverse Laplace. Well, my claim is that it's going to be the step function. So this exponential in the s domain is going to correspond to a step function in the time domain. And here we just find the inverse Laplace of f, but then we evaluate it at d minus c. Sometimes this is written as little f corresponding to the inverse Laplace of big F. But then we replace c at t and then just replace it with the t minus c. Indeed, you can check that this works because if we take the Laplace transform of step function times f at t minus c, we said that the step function corresponds to this exponential in the s domain. And then we would find the Laplace transform of f, where we replace t with t plus c. We already have a minus c there, so this works out. This is by definition big F at s. So for example, okay, so the inverse Laplace, this exponential will become a step function in the time domain. It gets turned on at 2. Consider the inverse Laplace of this function of s. It looks like it'd be, it looks like 1 over something cubed, so that looks like Laplace transform of t squared. Of course, then we would need if this is power 3, we need a 2 factorial in the numerator. So we introduce a 2 in the numerator and the denominator. We use linearity of the inverse Laplace transform. This is going to be t squared, except that there's a plus 7, so that means there was an exponential. So according to our formula then, the exponential became this step function, and then we found the inverse Laplace of this factor, but then we have to replace t with t minus 2. So let's do another example of finding the inverse Laplace. Inverse Laplace of e to the negative pi s times s divided by s plus 1 squared plus 4. This becomes a step function in the time domain. Then we're going to find the inverse Laplace of this. So let's call it f. So f of t is the inverse Laplace of this function. But we're going to replace t with t minus pi. So let's focus on finding the inverse Laplace of s divided by s plus 1 squared plus 4. So you're looking at the table of Laplace transforms to do that right now, and that should remind you of like the Laplace transform of sine of just some sort of sine, right? But with a shift. So what I'm going to do is I have s plus 1 in the denominator. I actually would like to see a s plus 1 in the numerator as well. So we're just going to introduce that by adding and subtracting the 1 in the numerator. Go ahead and write 4s2 squared. Then we break this up into 2 separate. I would then introduce a 2 in the numerator here. And of course introduce the 2 in the denominator as well. And we have the linearity of the inverse Laplace transform, allowing us to take the inverse Laplace of one term at a time. Again, using the table, this looks like cosine, but shifted over by -1. So that's going to be negative e to the negative t times the cosine of 2t. While this looks like it's the sine of 2t, but shifted by 1 and by -1, so we're going to have that exponential that does the shift, sine of 2t. But we're not done, of course. So we have to come back over here, and we said that we have our step function, and then we focused on finding inverse Laplace of big F of s. But then we got the result, but then we got to replace t with t minus pi. So I'm going to factor out the exponential. Okay, so there we go. So the next example, we're going to solve a differential equation with initial values, where the right-hand side function is piecewise. The function is equal to, so it's 0 before time equals 1. It is 1 between time equal 1 and 3, and it's going to be equal to t afterwards. Y at 0 is 1. Y prime at 0 is 0. So we're going to use Laplace transform to do this, but before we do that, we have to rewrite this piecewise function as a single expression using step functions. Function is 0 before time equals 1, so you don't have to write anything. At time 1, we're just going to turn this function on, so times 1. If you'd like, minus the preceding piece of our piecewise function, so that's 0. But then, the next transition time, t equals 3, so we're going to multiply by a step function that turns on in 3, and its job is will be to turn on the new piece, t, but subtract away the previous piece. Our piecewise function now is on the right-hand side is a single expression. So now we have to take Laplace transform of both sides. Take care of the left-hand side. So the Laplace transform of y double prime. s squared times big Y, it's a function of s, minus s times y, little y at 0, minus little y prime at 0, plus, using linearity, we get the Laplace transform of y, big Y. Might as well use the initial conditions. Little y at 0 is 1. Little y prime at 0 is 0. We are now going to take the Laplace transform of the right-hand side. So you have the Laplace transform of the step function, e to the minus cs. So c is 1. E to the minus 1s over s plus the Laplace transform of the next term. We're just going to get the step function becoming this exponential in the s domain. And then we get to multiply by the Laplace transform of this function where t is replaced with t plus 3. You still have a minus 1 here. Okay, so the Laplace transform of t plus 2 times the Laplace transform of 1. Do some housekeeping on the left-hand side. Try to isolate y on the left-hand side. So let's bring this s term over. To isolate y, we're going to divide both sides of the equation by s squared plus 1. I'm going to group these by the exponential. So each exponential has its own little factor group. Break up the rational function into a sum of simpler rational functions. So this turns out to be, it's like s, this is s squared plus 1. So if I did partial fractions here, I would get that. So I'll leave that fun part up to you if you want to derive that yourself. And then the partial fractions on the next rational expression here in orange. We want the s squares to cancel out. So yeah, there we go. That's the orange part. And then, well, the partial fractions on the next term here is exactly the same as this, except for the 2 in the numerator, right? So that would be plus 2 over s minus 2s over s squared plus 1. So wow, okay. But we are all set up, right? We're all set up to take the inverse Laplace of big Y, the function of s. All right, so first term. So that's going to be, it looks like it's a cosine of t. Second term. Well, we have this exponential. So that's going to turn to a step function which turns on at 1. And then let's just look at the inverse Laplace of 1 over s minus s over s squared plus 1. So that would be t minus cosine of t. But because of this, the formula we got is that we evaluate this inverse Laplace where we at t minus the c, minus the c, which is 1. Oh, hold on 1 second. The Laplace transform of 1 over s is just 1. And then we get cosine of t, but t is replaced with t minus 1. Plus, now the third thing, we get the exponential here becomes a step function that turns on at 3. And then we look at the inverse Laplace of all these terms. 2 over s plus 1 over s squared. And then you got your, so 2 over s, that's just 2. You take the inverse Laplace. 1 over s squared, that inverse of that is t. And then this becomes a sine of t. This becomes 2 times a cosine of t. But then again, remember, we have to evaluate this inverse Laplace at t minus c, c being the 3. So 2 plus and then t minus 3 minus sine of t minus 3 minus 2 times cosine of t minus 3. And I mean, that's it. It's a solution, no? We have time for another example. So first job is to turn that piecewise function into a single expression. So next, take the Laplace transform of both sides. Using on the left-hand side, using linearity, we get Laplace transform of y double prime, and minus 2 times the Laplace transform of y prime, plus the Laplace transform of y, which is just big Y, a function of s. And on the left-hand side, again, we have our step function in the time domain becoming this decaying exponential in the s domain. And then we're going to multiply that by Laplace transform of this function, except we're going to replace t with t plus pi over 2. So before maybe taking the Laplace transform, just use the fact that sine of t plus pi over 2 is just negative cosine of t. I'm using this fact. So we get negative 2 times the Laplace transform of sine of t. Beautiful. And then we have initial conditions. Y at 0 we said was 1, and y prime at 0 is also 1 if I'm correct. Okay, so you have gather the terms that have a y in them. So you get s squared minus 2s plus 1 times big Y. And then the remaining terms would be minus s minus 1 plus 2. Oh, this is a factor. This can be factored into a perfect square. We isolate y on the left-hand side, then divide by s minus 1 squared. We're almost ready to take the inverse Laplace. Here we just reduce. And over here, well, we have to do partial fractions. Some a over s minus 1 plus b over s minus 1 squared plus some linear factor cs plus d divided by this irreducible quadratic factor. It's a partial fractions interlude, so we want the original rational function. So let's gather the s squared terms on the s cubed terms on the right hand side. So you get an a, the s squared terms, the s terms, and the constant terms, so minus. So apparently, like if you compare the two polynomials in s on either side, for the two sides to be equal for all s's, a plus c has to be 0. A likewise, this coefficient has to be 0, but then c is the negative of a, so you get a plus b plus d is 0. So a plus c minus 2d equals 2, but c we already know is the negative of a. So this means the d has to be negative 1. The constant has to be 0 as well, as there's no the constant on the left-hand side is 0. So, okay, so looking at that, we get a plus b is negative. A is 0, b is 1, c is 0, d is negative 1. So now we're ready for the inverse Laplace. Okay, and of course, on the left-hand side, the inverse Laplace of this function of s is just the corresponding function of t in the time domain. The inverse Laplace of the first term we recognize as an exponential, e to the t. Inverse Laplace, well, here we have a decaying exponential in the s domain. So that's going to correspond to a step function that's turned on at pi over 2 in the time domain. And here the inverse Laplace of, let's focus on that. So the inverse Laplace of the first term, t, but shifted over by 1, so we have e to the t times t. And then this looks like sine of t. But back to our original, right, because of this step function, we have to replace t over here with t minus pi over 2.